The AMAZE project is about developing metals AM processes so they can be exploited by European manufacturing industry. It is the most ambitious and largest metals AM project in Europe. Additive manufacturing, often referred to as 3D printing, was first introduced to the production of rapid prototypes almost 30 years ago. Additive manufacturing parts are formed by the precise sequential deposition of layers of material. Additive manufacturing offers significant benefits over conventional manufacturing methods. Complex parts can be formed with relative ease, including high-performance parts incorporating lattice structures. It's a highly efficient use of materials. Producing complex parts using conventional methods such as machining can waste more than 80% of material. Another major benefit of additive manufacturing is that parts can be printed on demand without the need for tooling, giving unrivaled flexibility and allowing cost-effective, low-volume production, including one-off customised parts to be made. Novel combination of materials can also be used, which would be difficult if not impossible using conventional manufacturing methods.
So work package 2 of the AMAZE project had 3 overriding objectives. So the first objective was to conduct a market assessment of suppliers for additive manufacturing powders. The second objective was based on these supply chain analysis was to identify the suppliers which provided powder of the right quality for additive manufacturing. Then the third objective was based on this benchmark to create a standard specification from which powders could be quality controlled so that all the powders sent into the AMAZE program had the same starting characteristics.
The key objectives of Work Package 3 are to compare both powder bed and DD processes. In case of powder bed processes, we're looking at electron beam and laser fusing processes. And in case of DED, we're looking at both laser and electric arc deposition techniques.
Work Package 4 is dealing with post-processing of AM-made parts, and contrary to the widespread opinion that additively manufactured parts are directly ready to use after they have been built, is not correct. And a number of processing steps are required to process and to finish parts, for example, like this. This part has been undergone topology optimization, has been made by additive manufacturing approaches, but it is not ready to use. You have to prepare some elements here in this area, you have to polish it and so on. And Work Package 4 is dealing with post-processing.
Work Package 5 itself is concerned with adaptronics, in-situ sensors, non-destructive testing and metrology. And for equipment makers, it's really to make sure we can improve the quality of the machines and the parts that come off the machine.
So the objective of Work Package 7 is to manufacture demonstrator components for the project. And a second, equally important goal is to develop additive manufacture factories across Europe.
So here at the National Centre for Additive Manufacturing at the MTC, we have an EBM cell where we have a number of machines that were used to create the demonstrator parts in the AMAZE project. We also use the machines to develop the information for factory simulation.
So in Work Package 9, we're looking at industrial and environmental analysis. And we're looking at these impacts across the additive manufacturing supply chain, which is represented in the project. So we had a number of sequential activities that we worked on as partners. The first one being a database that brought together all of the information within the project. Particularly, we were focused on technical information for the materials as well as their performance after being processed. We're looking at some of the economic costs that we've already talked about, obviously looking at environmental impact as well, and also socio-economic impacts.
And in work package 10, which I'm the work package coordinator, we're involved in the processing of new alloys, as well as the production of metallic lattices for selective sound damping sonic crystals and for catalyst supports.
So, after 4.5 years, what has the AMAZE project achieved? It is the most comprehensive project on metals AM ever undertaken in Europe. It's provided end users in the project and European industry at large with robust additive manufacturing processes which offer high productivity and lower defect levels. It's also helped to develop new standards which will underpin the emerging industry. The new scientific developments and discoveries made in the AMAZE project by the academic partners have led to world-leading publications, which will also lead to new research which will help to provide the long-term future of the AM sector in Europe.